Milton?
Yes. Yeah, maybe.
Okay.
So welcome everybody. So it's a pleasure to introduce Cator from how do you say that? Nijmegen.
Radboud University Nijmegen. Yeah.
Nijmegen. Very good. She's going to talk about the periodic PNG model is solvable.
Thank you, Milton. And of course, also thanks Pablo for inviting me, although he was a little bit self-serving, I think, since it's joint work with him. So it's always good, of course, to give a talk about that. So I visited Pablo this May, I think. I spent a week in Buenos Aires and we worked on this. It was a very nice problem. And we found some very nice solutions. So I hope you will enjoy it. It's a light talk. It's not very, very heavy, but it's cute. And there's some very nice results, I think. So we're not with that many, I see. So please, if you have any questions, interrupt me and I'll be happy to answer them. We're in a relaxed atmosphere, so there shouldn't be any problem. Okay. So I wanted to start by introducing the PNG model. And I could do that by quoting the original paper by Prehoven and Spoon, but in fact, I had some different way into this PNG model because, no, that's bad. That's better. Because, I did some work on the Hammersley process and it's very closely related to the PNG model. So just for old time's sake, I wanted to start with the Hammersley process. And here you see a picture of that. You should think of the horizontal line. Can you see my mouse? Yes, excellent. So you should think of the horizontal model as the horizontal line as space, and on this space there are particles. So here and here is a particle, and a couple of particles in space. And the vertical direction is time. So as you move up in time, you can see that the particles they jump to the left, and they jump to Poisson points that they encounter. So in the plane, there's these red points, and they are a Poisson of intensity 1. And as you move up in time and you encounter one of these Poisson process, then the first particle to the right jumps to it, and then it stays in place until it jumps to the next Poisson process. And then you get these paths going from left to right. And there are a lot of things known about this Hammersley process. For example, in the stationary version, if you take the horizontal line, then it's an independent Poisson process of a certain intensity, let's say lambda. And then if you look at the vertical line, you look at the crossings there, that's also in a Poisson process, and it has intensity 1 over lambda, so that the product is 1. And another nice feature is that the Poisson process here on this part, and then if you go up like this, then this part, these two Poisson processes are actually independent. That's all very nice. But that's not what we're going to talk about. What we're going to talk about is this picture here, where I've just rotated the previous picture 45 degrees. So now the interpretation is that time goes up in this direction. And then again, there's an horizontal line, and this would be space, but you get a different type of process. So let's see what it looks like. So here we have space. And now if you look at the crossings with the blue lines, you can see crossing going to the right. We will call that a positive particle, and you have crossings going to the left, and they are negative particles. So you have a couple of negative particles, then some positive particle, and this is the particle configuration. And as time goes up like this, you get a new configuration, and you can see that the positive particles then move to the right at unit speed, and negative particles move to the left at unit speed. And then two other things can happen. For example, here, you see if I can zoom in. So there's a positive particle and a negative particle, and they bump into each other and they annihilate each other. So there's annihilation. And here's also a nice example that this is one of the Poisson points from the previous picture. And there a pair is created, a pair of negative and a positive particle, and they move away from each other in time like that until they again get annihilated. Now, so there's annihilation and there's creation of these pairs. And once they are there, they move in a deterministic fashion, either to the right or to the left. Well, of course, so this is, it's basically the same model. It's just a rotation. So a lot is known about this as well. And later on, so when I first gave this talk, I got a question from Martin Ballach, and he recognized that this was in fact the PNG model introduced by Prehoven and Spoon. And this creation, it's like the growth of a little little surface that moves like this. And then when two surfaces meet, they merge, and that's the annihilation that you can see here. And for example, what is known is that if you look on this line, the positive and negative particles, they form two independent Poisson processes in a stationary case. And that's also something you can prove through the Hemsley process if you want. Okay, so that's very nice. But we want to restrict this model and want to see if once we restrict it, what can we say about the model? Because it's not so clear anymore that it's still solvable. And Pablo came to this model, this restricted PNG, this periodic PNG model, as some limit of a discrete problem he was looking at. And if you take a certain limit, you get exactly the thing that we're looking at now. But it's very clear that there's a relationship with the original PNG model. So what do? We restrict the length of the space, and we go from 0 to L, and you should think of this as a circle. And then we have positive and negative particles. Now we will enforce that these numbers are the same. If you have the same number of particles, you get some interesting ring structure that I will show you later. You can also try and say something when it's not the same, but this is, I think, the most interesting case. So we will restrict ourselves to that you have the same number of positive and negative particles, and then they move. But now, of course, in a periodic fashion, they move. The positive particle moves to the right and the negative to the left. And when they meet each other, they annihilate like before. And then you have this Poisson process, but now on the cylinder. You have the circle and time goes up, so you get a cylinder. And on you have this Poisson process, and that's where a pair is created, a pair of positive and negative particles. So that's the idea of the periodic PNG model. And so we introduced the state space for this. It's not so complicated. And what you need to do is you need to give, if there are n positive and n negative particles, they have positions. So those are these x's. And of course, the negative ones also have positions. So you need another copy of this delta n. So that's here, delta n times delta n. You take a union from n is 1 to infinity. And then it's also possible there's nothing. The empty configuration is also possible. So this is the state space of this process. Okay. Now I was talking about these rings. So you have to kind of figure out what this means. So if you have this configuration here, then here's a positive particle. And this positive particle is linked to this one, this red one here. And the way you can see this is that, if you move to the right, you first get another positive particle, but this one will be linked with this negative particle. So that's why they're both blue. And then this negative particle is linked with this blue particle, blue positive particle. And then you go to the right again, and you encounter a new color, which is like brown. These two get annihilated. Then this blue one annihilates with this one. And then finally, this red one will meet this one. So you see three colors here. That means that this is a crossing of three rings. And also, it's obvious that it should be rings because this negative one should be linked to the next positive particle, which is, again, this one. And so they are linked on top like this. They go up like this and then go down. And then this goes down. And then, because it's periodic, it will encounter this one again. So if you make a picture like this is a simulation of, let's say, 20 seconds of these rings. And what you see is that they form closed loops and they're separated from each other, all these rings. And if you look at this picture, there are several questions you could ask about this process and to think about how, what is the exact structure that we're looking at here. So you see the black points, those are the Poisson points, which is intensity 1 on the cylinder. And we started with the empty configuration in this case, and these black points, they give rise to these paths like this. And then there are green points. Those are the points where a positive and negative particle annihilate. So you might call them dual points, and maybe we have some structure there as well. And well, we will see. But the first question we have to answer is, if you now take a horizontal line, let's say far above, somewhere here, what is the structure of the particles that you will see? What is the stationary measure of this process? Okay. So, well, first we introduce a dominating measure, which is kind of the obvious one. You got this space delta n times delta n. So we just take the Lebesgue measure on one of these deltas, and we make sure that they have total volume 1. So that's like this. I guess I forgot also the y's. There should also be dy1 to dyn there with the same factor. And then on this product space, you get that this part of the state space has measure 1, and then you give measure 1 to the empty configuration, and then there's the dominating measure. So each, of the possible number of particles has total weight 1. And now we have to make a guess for the stationary measure. And well, let's see. We know that in the case where we have L is infinity, so the non-periodic case, we know it's just a Poisson process. And now maybe it's again something Poisson, the number of points, but there's a subtlety here because they're positive and negative particles, and they should be the same. They should have the same number of positive and negative particles. So a natural guess is we just take two independent Poisson number of random variables and we condition them to be equal. Then you get this. So you have x and y. X is, let's say, the positive number, and y is the number of negative particles. They have some parameter lambda, take them independent, and then we condition them to be equal. So it's like this. And that gives you a distribution. And maybe the distribution has a name, I'm not sure, but we just called it the Poisson square distribution because you get the Poisson probabilities, but they're all square because, because of the condition. Because they have to be equal, x and y. So, and our guess is that this is the distribution. So you first think about the number of negative and therefore also positive particles. And we take this Poisson square distribution. And then, of course, once you have the number, you just throw them uniformly on the ring, and that should be the stationary measure. And this would be consistent with the limit for L going to infinity, at least. So that's nice. But of course, that's not really a proof that this should be the correct one. So here's a theorem. This is actually true. And this is, like a little bit of a miracle, of course. You just guess something and you hope it works, and it turns out that it does. So that's very nice. So we take, as a stationary measure, we take this mu n, and we give each size n, we give a probability p of lambda n, which is given by this Poisson squared distribution. And then lambda has to be something specific. So we don't have a choice in this. It turns out it has to be equal to L over square root of 2. And the square root of 2 is actually quite natural because if you remember, we have turned around this heavenly picture. And by turning it around, you get this kind of extra factor of square root of 2 in there, because the length doesn't correspond anymore. But that's some heuristic explanation why there should be this factor square root over 2. Okay, so how do you prove this? Well, let's take a slightly heuristic approach for this. So we assume that x0 is actually distributed according to this mu, and then we want to prove that the distribution at time h, or some small h, is also the same as mu. And what we're going to do is we're going to show that the corresponding probability or the corresponding density for x of h is indeed equal to mu up to a factor small order of h. And this will be enough to prove that mu is a stationary measure. Okay, so why is this true? Let's first start with what is the probability that there's the empty configuration at time h. So there are two possibilities how this could happen. Either you, at time 0, you start with the empty configuration, and then you want to, keep this empty configuration up to time h, and that means that there shouldn't be a creation of a positive and negative particle in that point. Right? Should be no creation. Now the probability of finding a Poisson point in length L and height h is of course h times L. So you get p lambda 0 times a1 minus HL. So that's the first option to get an empty configuration. The second option is that, in fact, you had one positive and one negative particle at time 0, and they just happen to annihilate each other. When they annihilate each other in time, then you get the empty configuration at time h. So how can that happen? Well, you have to, the positive particle moves at unit speed, the negative particle also, so they approach each other at speed 2. And that means that if these two particles are at distance 2h of each other, then they will annihilate it, and in the right order, of course, so the positive left and the negative to the right, then they will annihilate each other. And of course, the probability of that happening is in fact 2h divided by the total length of the circle. So you take a configuration with two particles, a positive and negative one, you enforce that they're close together, and then they're annihilated at time h. So that's the other possibility. And of course, by the choice of p lambda, this happens to cancel out. So the h times L times p lambda 0 cancels p lambda 1 times 2h over L exactly when lambda equals L over square root 2. And because you get a lambda squared difference in this in these two probabilities, and that's L squared over 2, and then this cancels well, in the right way. So that's nice. Now this is only for the empty configurations, and now we need to do this for a general configuration. So suppose we have n bigger than or equal to 1, we have some positions for the positive particles and some positions for the negative particles, and we want to see what is the probability that at time h we get exactly that configuration. So how do we do that? Well, again, there are two possible ways to do this. The first way is that, in fact, at time 0, the positive particles, they were at the same position but shifted slightly to the left, so that at time h they're in the right position, and the negative particles, they're shifted slightly to the right, so that at time h they're also at the right position. So this is the configuration at time 0. And then, of course, again, there shouldn't be any creation in this period. There will not be an annihilation, because if h is small enough, they won't have time to annihilate each other. So you only have to ensure that there is no creation in this time. Okay, so that's this factor here. And of course, you realize that the density for x and y is the same as the density for x minus h and y plus h, because we have uniform distribution. So that should work out nicely. So that's one possibility. And then the other possibility is that, in fact, you had n plus 1 positive ones and n plus 1 negative ones, and a positive and negative one will annihilate each other in time h, and then you end up with the right set. So how can this happen? Well, take n plus 1 particles, positive and negative ones. Let's say we put the first positive one at x1, the second one at x2, and then the nth one at xn. And for the y's, we do the same. So then you get this factor here to make sure that happens. dx1 over L, dx2 over L, dy1 over L, dy2 over L. You get this factor here. And then you end up with the n plus 1 two particles. And they again have to be close together so that they annihilate. So you get a 2h over L for that factor. So then they will annihilate and will be gone after time h. And then of course you can, interchange all the positive particles and interchange all the negative particles, and it won't make any difference. So that's an n plus 1 factorial squared. So this is the way this will happen. And then you have a small order h correction for this, after this. Okay, now again, you can make this calculation here. So this part, the density of being in this configuration, well, it's exactly here. It's p lambda n, and then times this the dominating measure at n particle position. So that's this factor here, and then that gets multiplied by h times L like that. And we have this other factor here on the right. And of course, what happens, and I didn't show this. So here, there should be an extra factor p lambda of n. So p lambda n plus 1 equals p lambda of n times an extra factor of lambda and also an extra factor of L. Is that true? No, it's the extra factor of lambda, and there's the n factorial, the n factorial squared, n plus 1 squared. That's also an extra factor. So you end up with p lambda n, and you get this extra factor of lambda there. And if you look at these two terms, they cancel exactly, and therefore you end up with the correct probability. So here should be an extra factor p lambda of n. My apologies for that. Okay, so that's very nice. So it's relatively straightforward. You just have to figure out how do you get to a certain configuration after time h when you know the configuration at time 0? Okay, that's good. So we have, it's a solvable model apparently, and we have a stationary measure. But there are more questions that we could answer when you look at this picture. And the first one, kind of obvious one, is these green points. Right? These are the points of where they annihilate each other. And we know that if you look in the PNG non-periodic case, there you also have these green points. And in fact, you can look at the reversible model, and these green points, they form a Poisson process. And there's what they call the Burke's theorem for that case. So it would be nice if we have that here as well. And it turns out to be true. So we can prove that these green points, they form a Poisson process on the cylinder with intensity 1. And in fact, we can do one statement, make it a little bit stronger. So the dual points, they form a Poisson process, but it's in fact independent of the configuration at the final time. So that's, you should think of this as a reversibility theorem, because you can start at the top and then you go down, and these green points, they're independent of where you start. But of course, the green points fix the entire configuration. Just in the same way as you go up. You start with the configuration, you have the black Poisson points, then you know the entire configuration of the path. So here it's the same. So if you prove that these Poisson points are independent of the final configuration, then you have a reversibility theorem. Now, how do you prove this? Well, it's actually very similar to what we did before. So that's the stationary measure. So you look at the probability that there is a dual point in some interval in space, AB, so that's part of the circle. And then you have a small time interval, t minus h times t, on top. And in this small rectangle, you want to know what is the probability that there is a Poisson point. And if it's indeed a Poisson process, this probability should be equal to the size of the rectangle, b minus h times the height h, up to smaller order, of course. So that's what we should find, but we can actually calculate it, at least so what we're going to do is we're going to condition on the top part, and then we're going to show that for any type of conditioning, we get the same probability, so then we get the independence for free, if we would do that. So we condition on the final part to be empty, and then we wonder, how can it be that there's a Poisson dual point? So that means that there's an annihilation. Well, if there's an annihilation in between time t minus h and t, it means that at t minus h, there should have been 2 points, and they should have annihilated in a certain place. Right? And once they have annihilated, then there will be the empty configuration at time h, and you will have a dual point. So that's exactly what should happen. So that's what it says here. We get p lambda 1. So you have one positive and one negative particle. The positive particle should be somewhere in this b minus h. So that's b minus a, sorry. So that has probability b minus a over L. And then the negative particle should be no more than 2h away from this positive particle. So that has probability 2h over L. And then here you divide by p lambda 0 because of the conditioning. So you got this conditioning, so that's why we divide here. And then if you calculate this, you get exactly a term lambda squared, and the lambda squared cancels against the 2 over L squared, and you end up with b minus a over h. So that's good. And if you have a more difficult conditioning, it's actually very similar to what we've seen before. So here we have a general conditioning that you have some configuration z at time t, and you want to have a dual point in this interval AB and this small time interval. And then you realize that this can only happen if at time t minus h, you have the same configuration, but you get these 2 extra points that annihilate at the right space. So at the bottom, you get the conditioning density. At the top, you get one positive particle more and one negative particle more. The first n particles, positive and negative, should be in the space, should be in these places, the x1 to xn, y1 to yn. And then the last ones, they should, again, like before, be in the interval b minus h and not more than 2h away from each other so that they annihilate. And then you get the n plus 1 factorial squared because you can interchange them. And then if you calculate this, you exactly get the same answer as before. So this is very nice. And this proves that the green points, in fact, the whole process is reversible. I mean, if you look at the picture, it seems very obvious, but of course you have to make some calculation for this, and it turns out it's not too hard. So this is, looking nicer and nicer, and we get more and more results for this periodic case. Now, we need to go back a little bit to this Poisson square distribution. It turns out that if you want to know what is the expectation, or what is you have these probabilities, these squared Poisson probabilities, but they don't sum to 1 anymore. So you have to correct that, and this correction factor turns out to be these modified Bessel functions, and so you get I0 and you get I-1 for the expectation of the number of positive particles, for example. But the squared number of particles, so the expectation of the square, that turns out to be easy. That's just lambda squared. And you can look, the probabilities, they have this factorial squared in the numerator. So if you multiply this by k squared, you get k minus 1 factorial squared. And that's why you can just make shift something around, and you get an easy answer for the expectation of the square. And this turns out to be relevant. So I will come back to this. There's a reason why I want to show you this result. Okay. So again, we have this picture. We now know if you take a horizontal line, what is the distribution? We know that the green points are Poisson. We want to know a little bit more. For example, one natural question here is to ask, how many rings will I get? If I wait for a long time, what is the expected number of rings? And we have to realize, for those of you who kind of are familiar with the PNG or with the Hammersley process, this time, that's the interesting direction for the Hammersley process. So that's where you get cube root fluctuations and Tracy Widom and all these kind of things. So that kind of shows that also in this periodic case, there should be something non-trivial about going up in time and looking at the number of particles. But if you're only interested, or the number of rings, but if you're only interested in the expected number of rings, that's like comparable to Ulam's problem. So that's solved for the Hammersley process. So it's feasible that we can solve it here as well. And we can. So we can look at the expected number of rings in the time period 0 to t. And we can calculate exactly. So how do we do that? Well, we are in the stationary case. So if you take a vertical line, so that's a line in time, which is what you see here at the bottom, then you can wonder, what is the probability that between t and t plus h, there is a crossing, there's a particle through a ring going through this line? Well, there are two options. It's either a positive crossing or a negative crossing, like here on the right. And can we calculate the probability of that happening? Well, as you can see, if you want to have a positive crossing here, that means that if you follow this line, then in this space, so this is the space direction, in this space direction, you should have a positive particle, and that will cross this horizontal line. And of course, here we know the stationary measure, so we can actually calculate the probability expectation, the expected number of positive particles in this interval. So that's what it says here. Yeah, you need to know the number of particles here, and of course, on the right-hand side for the negative ones, the number of negative particles on this right-hand side. And then you can just calculate the expected number of rings. And it turns out that, well, it's this formula here. 2 times T over L times the expected number of positive particles at any given time. That's the expected number of rings from 0 to T. And this is exact. This is not only true for T going to infinity, this is true for any T. So that's nice. And we can take this one step further. Because now, if you look at the number of rings, each ring has a certain shape. Let's look at the picture again. So you see that a ring has a certain shape, and one of the characteristics of these rings is how many minima the ring has. So for example, this ring here has 2 minima, but this one has 1, 2, 3, 4 minima. And of course, you always have at least 1 minima, but there's no maximum. So the number of minima of these rings is some characteristic of this process. and maybe we can say something about this. And what we notice pretty soon is that if you know the number of rings and you know the total number of Poisson points in a rectangle, then of course, if you want to know how many minima are there in each ring, you just have to divide the number of Poisson points by the number of rings. And that will give you, for each ring in the stationary case, what is the expected number of minima? And if you do the calculation, then we use that the expectation of W squared equals lambda squared. I showed you before. So then you get this relationship. So let me do a small recap. W is the number of positive particles on a horizontal crossing. And N is the number of minima in one of these rings. So one ring, of course, is not fixed in time. It covers a period in time, but it is one ring, and you can look at the number of minima, and they are related in this way. And now I wanted to ask you if this rings a bell. So this relationship between N and W, where the expectation of N equals the expectation of W squared divided by the expectation of W. Is there anyone who finds this familiar? Okay, we're all a bit shy. Milton. I cannot hear you.
No,
now I can hear you.
I think I've seen it in a random tree somewhere there. No. Yes,
that's where you see it as well. Indeed, in random trees, what happens is that if you go to a neighbor, right? You find a certain node, and this node will have a lot of neighbors because that's why you find it. So you get a size bias in the number of nodes that you find, and that's exactly what happens here. So very good. I had a similar thought. So if you look at this Poisson square distribution, and then you take the size bias version of that, then this will have exactly the correct expectation, at least. Well, if you have the correct expectation, of course, the conjecture is easily made. You would just conjecture that the number of minima is equal to the size biased squared Poisson distribution with the same parameter lambda. That's what you see here. So this N, what does mean? I'm sorry, I have to maybe repeat what it means, size bias. It means that the probability gets weighted by the size of the number of points. So here's the Poisson square probability, and you multiply it by K, and then you get the size bias distribution. And of course, you have to divide by the expectation, in fact, of W to make sure that it still sums to 1 if you do that. And we call this P star. So we had P of lambda, now we have P star of lambda, which is this size biased squared Poisson distribution. And the conjecture is that if you look at the stationary case and you look at these rings, then the number of minima in these rings follow this size bias distribution. Well, I'm a hands-on type of probabilist, so I decided to simulate 100,000 of these rings and just count, how many minima do we have. So that's here, you get a nice histogram, and then I calculated the Poisson square distribution, the size biased Poisson square distribution, and then you get this. I'm not sure if you can see it, but here there's a little red line, and that's the theoretical one, and it's pretty close to the black one. I think here you can see the slight difference between the two things. But of course, this is very convincing that our conjecture, well, it just should be correct. There's no other way. So that's nice. And if we have one conjecture, we can continue to the next conjecture. Oh dear, I screwed it up. Now, there you go. We can continue to the next conjecture because if I know how many minima a ring has, well, then I can guess what is the entire distribution of the ring. Because you just do you put them down uniformly, these minima, and then once you know the position of the minima, you know the entire ring. So, what other option do we have? We just state that this will be the stationary distribution of the entire ring. So then we would know what these rings look like. What is the distribution of these things? So that's nice, but that was also slightly challenging to actually prove this. So that will be the final part of my talk, trying to convince you that this is actually true, that this conjecture is, that we've actually proved it. And in order to do that, we need to have some tools, because, well, these rings are slightly complicated things, right? They're not just particles on a line, they have some structure, and you have to be careful. So it turns out that we can describe each of these rings with the same state space as we had before. And so that's the state space where you have either the empty configuration or 1 particle, 2 particles, 3 particles, and a copy of those. That's the state space, the same as before. And here is a picture how this works. So this is an example with 2 points here, and 2 points means 3 minima. So the empty configuration has 1 minima, and then you know exactly what the path looks like. And if you have a configuration with several points, then the number of minima is 1 higher than that. Okay, so here's an example where we will get 3 minima. We take 2 points for the x direction. We take 2 points for the y direction. It's not so obvious anymore whether this is a positive or negative particle. That's not really how it works. It's more, how do we move in the cylinder? So what we're going to do is, we have these 2 points on the y and these 2 points on the x direction, and this red line here, that describes the path. So you start somewhere, you go up until the first y, then to the right till the first x, then to the y, x, then y, and again, and then to the final corner. And this final corner, of course, is the same point as this one here, because it's periodic. So what we do now is we rotate it 45 degrees, like this, in a negative direction. And then you get this picture here. That's how we're going to do it. That's how we're going to describe the path in the cylinder. And there's one more thing I want to show, that this point, the starting point, always corresponds to the point 0, 0 in the cylinder. So time 0, the time, of course, not so relevant, but also the space, we just take the point 0, that's where we start. And therefore, this point will always be a minimum, sorry. So if you have the empty configuration, the picture you would see is you go up, 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 up until here, and you go down, down, up to there, and then it's just one mountain, let's say. And it has exactly 1 minimum. And remember, this is a circle, so you have to keep this in mind. And these 2 points here are connected. And therefore, this green point, is indeed a forced minimum. But that's how we go from the state space to the cylinder, and we call this map, it's a bit ugly, but it's called a phi. Okay. So let's just, these state spaces of rings has, each path in this state space has 3 features. The first one is sigma n, which is the number of minima of the final path. So this is always bigger than or equal to 1, and it's actually 1 less than the space, than the dimension of the space you're in. And then if you have indeed 2 or more minima, then you get sigma n minus 1 points on the x-axis and sigma n minus 1 points on the y-axis, just like in this picture here. So here sigma n is 3, and that's why you get 2 points on the x and 2 points on the y. Okay. And then phi sigma, that's the corresponding ring in the cylinder that starts with a minimum at 0, 0, and then it follows this path and you get the ring. Now, it turns out that you can actually describe what is the position, the 2-dimensional position of the other minima of this path, and that's given by this formula. So minima pi is given by this formula here. Of course, it's possible there's only 1 minimum. That's also fine. Then it's at 0, 0. Now, what is very relevant in this case is that in the cylinder, there's a Poisson process of intensity 1. So the volume measure of the cylinder is relevant for us because we have a fixed length L and we have to take this into account. And that's why we need to remember what is the Jacobian of this map, the map going from the space E to the cylinder. And the Jacobian, you can easily calculate it. it turns out to be 2 to the minus sigma n minus 1. It will come back in our formulas. Okay. Now we have the state space. Now we need to make a Markov chain on this state space. So what are we going to do? So we start with some path in E, which corresponds to a ring phi of sigma 0, and that's called R0. So sigma 0 is the path in E, and R0 is the corresponding ring with a minimum at 0, 0. And now we're going to make the next ring. So look at the picture. The red one is the ring we had before, R0. Now, above this red one in the cylinder, we create a Poisson process of intensity 1. And then it turns out you get these two black points here, and they're the only relevant ones. And in between, there are no black points. And that means that the next ring in our PNG periodic model is given by this blue line. This has to be the next ring. And you start new positive and negative particles at these times, and they meet up with each other, and then they form the ring. So that's the way you get R1, just following the rules of our PNG model. And now we have to map R1 back to our state space E, where we started. And this is a little bit subtle because, well, R1 in this case, for example, has 2 minima. And we have to find one minimum that goes into 0, 0. So the natural way to do this is to pick one at random. So we pick one of the minima at random, and we put that at 0, 0, and then we just kind of apply phi inverse. Yeah, so we find sigma 1, and we call it, which will be the phi star of R1. It's chosen in such a way that if you take R1, and then you pick one at random, and then you rotate and translate this to 0, 0, this minimum, then that ring that you get is exactly phi of sigma 1. That's how sigma 1 is defined. Yeah, so you pick one at random here, for example, this one, and then you rotate, you translate this back all the way to 0, 0, to this green point. So you turn it and you move it, and then you can take the phi inverse of that thing, and that's sigma 1. So now we have defined a Markov chain on our state space E, going from one ring to the next ring, let's say. And what we want to do is we want to describe the stationary measure of that process. That's what we want. And if we can do that, then we have found indeed the stationary structure of all these rings. So that would be nice. Okay, now, how are we going to do this? Well, we have to describe the transition kernel of this process. So for a transition kernel, you need a dominating measure. Well, we already had it. It was this nu. That's clear. And then the transition kernel should satisfy, of course, that if you integrate over the state space E over all possible outcomes tau, and then for any sigma that you start with, the total integral should be 1. And so that you have a probability 1 of finding some tau when you start at sigma. So we need to find this transition kernel. And how are we going to do this? Well, we're going to study the process on the cylinder, because that's where we actually know what's happening. So if you have two rings in the cylinder, let's say the R0 and R1, so that's the bottom one is R0 and the top one is R1, then we can define A of R0, R1, which is the size of the area between the two rings. So that's this area here in between, between the blue and the red one. That's A of R0, R1. And of course, this is only well defined if R0 is completely below R1. And if that's not the case, if R0 is not completely below, then we define A to be plus infinity. And this is just a trick. So, because you cannot find a ring that's not above R0, right? The next ring will always be completely above R0. So that's why we need this little, well, this small trick. Okay, now, fix R0, that corresponds to our fixed sigma here. We fix R0, and then the next one, that's a random ring, and we call it R1. And I want to know what is the probability that R1 the random one will be equal to some ring Q. Yeah? And a ring Q is determined by the position of the minima. So suppose we have a ring with n minima, and we place these minima at x1, y1, x2, y2, etc. That's the position of the minima of the ring Q. And then we have, we have the Lebesgue measure on the cylinder. So you have dx1, dxn, dy1, dyn. And I want to know what is the probability that my ring R1 is exactly Q plus this little d of z, right? It ends up in that set, let's say, in that space. And it turns out that's actually not that hard. You can just write it up, because what needs to happen is that you need to find Poisson points, right? These minima, if you look at this picture, the minima of this ring correspond to Poisson points on the cylinder. So there have to be Poisson points at the positions x1 to xn, y1 to yn. But it's a Poisson process with intensity 1, so that's very easily calculated the probability. It's just this big product. And then the other thing is that in between these two rings, there should not be any Poisson points. So that's this probability, e to the minus, and then the area in between these two things. Right? If there are no Poisson points there, and then there are Poisson points at these positions that you want, then the next ring has to be equal to that Q. Is this kind of clear? Okay, so that's quite nice, because we have an explicit formula, albeit in this strange, this strange area thing. So it's still a little bit complicated, but at least it's something explicit. Okay, so this is the probability of finding R1. Now, that's not what we're interested in. We are interested in the probability of finding some strange tau, right? Tau being a path in our state space E. That's what we are interested in, not some ring on a cylinder, but we have to go into the state space E where there's no horizontal nor no vertical direction. Okay, so how are we going to do this? Now, we take a sigma and a tau in E. Sigma is the fixed one when you start, and you want to end up in tau, right? Now, suppose tau n is n, so there are n minima, and then we have some neighborhood of tau in this space. Tau has n minus 1 x and y coordinates, so it lives in this space, and then there's just a Lebesgue neighborhood of this tau, which we call dz. Now, R0 is phi of sigma. R1 is the next random ring. And what I want to end up, near tau, somewhere in tau plus dz. So I take R1, I take our random map, phi star. It's a random map because I have to take a random minimum of R1, and then I find my tau. Yeah, so I want to know the probability that phi star of R1 equals this tau, given that we started in sigma. So how are we going to do this? Well, what I'm going to do is I'm going to integrate over all possible rings Q in our previous sheet, all possible rings Q that can give us this tau. So Q should have the shape of phi tau, but we can translate it in the cylinder, in either the x direction or in the t direction. Right? So we just take all possible translations of phi of tau, and then of course the only relevant ones are the ones that end up above phi of sigma, but we make sure of that in our definition of A, so that's fine. And so I take all these translations, and then once you have the translation, what needs to happen is that this area in between these two things should be empty. So that gives this probability e to the minus something. Also, you should have a Poisson point, at these positions, but don't forget, we need the Jacobian here because tau has a certain space to move in, but this space becomes smaller in the cylinder because of Jacobian. So that's this factor here. And you get Tn minus 1 because that's in fact the dimension of delta n minus 1. So you get this Jacobian. And then here there's another factor 1 over tau n, which is also interesting. 1 over tau n, that means that you pick the right minimum, right? Phi of tau has the right shape, but there's only one minimum that corresponds to 0, 0. So in your phi star, you have to pick that minimum, and that has probability 1 over tau n. So that's this factor here. And this should be the transition kernel. Well, actually, not really. This is the probability. So now I have to relate this to the dominating measure, mu, and that's why you get these extra factors here on the right. That's just because, that's part of the dominating measure. And then you get the final kernel. So it's an integral, there's a strange area here, and then you get these factors that make it the correct transition kernel. So these ones are just trivial, and there's 1 over tau n, that's because of this factor over here. Okay, so this is also nice. As long as you're very careful, you're able to write up the actual transition kernel of the Markov chain that we're looking at. Now, if you have the transition kernel, there's a chance that you can actually prove that you have the stationary measure, right? So we're going to use the following trick. So we have a transition kernel K, and we have some density F on E with respect to nu. And we want to show that F here, this F is the stationary distribution. Now, suppose I can find another transition kernel, K star, which satisfies the following two things. So the first one is just saying it's a transition kernel, right? This K star is a transition kernel. And the second one is more complicated. This is like a detailed balance type of equation. So K sigma tau times F sigma should be equal to K star tau sigma times F tau. So this is like a detailed balance equation. And now you can see that if you integrate this over sigma, that's right. If you integrate this over sigma, what do you get? Well, it says here, K sigma tau is the probability of ending up in tau when you start in sigma. So if you integrate this with respect to F of sigma, then you get the probability of ending up in tau given that you start with distribution F. So you start with distribution F, then if you integrate this over sigma, you get the distribution of the new tau. But if you do it on the right-hand side, if you integrate here over sigma, well, sigma is only here. And since it's a transition kernel, the first property tells us that integrating this over sigma gives 1, so you end up with F tau. In other words, the stationary measure, the new distribution of tau that you find is in fact the same as the previous, as the old one given by F, and therefore F is a stationary measure for transition kernel K, and in fact also for transition kernel K star. So what we need to do is we need to find some clever K star that that gives us this. And well, for those of you who have seen this before, there's always like a canonical candidate for this K star, and that's the transition kernel of the time reverse process. So what we're going to do is we're going to, instead of going up in the cylinder, we will go down in the cylinder. That will be our K star. And of course, our guess, well, we already seen it. Our guess for F sigma is just uniform measure. And then the probability of finding sigma and minima is equal to the size bias squared Poisson distribution, like this. Okay. So now we need to make a calculation. We need to see what is the reverse process K star. What does it look like? And so there's a little subtlety here. Instead of having sigma tau, I now write for my own convenience tau sigma. So I want to start in tau and go to sigma, but it's the reverse process. So just as before, sigma is below and tau is above, because we go from tau to sigma in a way going down. So how do I end up in sigma? Well, same trick as before. We take phi of sigma, which is the ring you need to end up with, and then I translate it down from Tor. So I go down with sigma, and then in order to find sigma, what you need to have is you need to have Poisson points at the relevant minima of this translated phi sigma, and in between it has to be empty. There should be no Poisson points. So that's this A of phi sigma minus xt phi Tor. And now, of course, you can kind of see why this might work, because going up from sigma to Tor or going down from Tor to sigma, well, it has the same area. The area is the same. So it doesn't make any difference, because that's the key here. Going up or going down, you look at the same area in between. So, we use the fact that instead of translating phi sigma down, you might as well translate phi Tor up like this. So now you end up with the same integral as we had before for our k. It looks the same. Of course, the factors now are related to the sigma, because we go to sigma, not to Tor. So that's why you get 1 over sigma n instead of 1 over Tor n, right? Because you end up in phi sigma, and you have to pick the right minimum for sigma. So that's why you get 1 over sigma n here. And also the Jacobian is the same. That's also, well, kind of obvious. That's the case. So we have a formula for k sigma. We have a k sigma Tor. We have a formula for k star Tor sigma, which is like this. And for the detailed balance, what you need to do, that's here, what you need to do is you look at k sigma Tor, and I will divide it by k star Tor sigma and see what comes out. That's here. K sigma Tor divided by k star Tor sigma. And as I mentioned, the integrals cancel, because we have manipulated them in such a way that this integral, they drop out. That's very nice. And then you end up with these factors here. So the k star has the sigma factors, and the k has the Tor factors. And if you fill that in the right way, it turns out that the top part exactly corresponds to p star of Tor n, with some correcting factor lambda to the -2. And the bottom part, which is the same, of course, but then Tor replaced by sigma, you get p star lambda of sigma n with the same factor. But these p star lambdas are exactly our density f, our stationary measure. So in the end, it just falls out and you get the correct answer, which is, I don't know, I still think it's a little miracle that we were in fact able to fully describe, if you look at this picture here, to fully describe the way these rings behave and how they look. We now have a full description of this and prove that this is indeed, for the stationary case, true. So what I'm hoping, well, maybe, I think these results are just nice in itself. And we have to realize that the periodic case, if you can prove solvability for that, that's stronger than the solvability for the non-periodic case, because one implies the other. And what might happen is that this is also some kind of determinantal process, and it might give some more detailed information about the case for L going to infinity. For example, what would be very interesting is to know the variance of the number of paths that you find between 0 and t. If you can have an exact formula for that, that would directly translate into an exact formula for the non-stationary case. So the fact that this is all solvable, we have these explicit formulas, and there's also that this might have some consequences for the non-stationary case as well. Okay, well, thank you very much for your attention.
Okay, so this is okay. So there are some questions. We have some questions here. So questions in the chat. Yeah, Sergio.
Hi, Sergio.
Yeah.
Hi. So do you have the intuition why the size bias distribution appears?
Yeah, that's interesting. We also thought about this, and we have no intuition. I mean, the only thing is this, the fact that I saw this, I kind of, prompted me to guess the size bias. And then I did this simulation, and it turned out to be exactly correct. So, we were very lucky in a way, but I don't really see, because you see, the W is the crossing with the horizontal line. But these paths, they don't live on a horizontal in one time, right? They live in space-time. So it's not so obvious how they are connected, these things. So I don't know. If someone has a good intuition, I would love to hear it.
Thank you.
Yeah.
So another question? Hey, Sundar.
Hey, hi, Eric. Nice talk. Maybe I could ask a question.
I can't see you. Is that correct? Or?
So you mentioned determinantal process at the end. What would that give us? Is that related also to integrability? Or?
Well, I would say that the fact that we have an exact formula for the stationary measure, not only for the rings, but also for the horizontal, for this positive and negative particle things, that kind of, for me, that's kind of equivalent to integrability of this model. Maybe that's not true, but that's my intuition for integrability. So I know that these determinantal processes, they are very important for all the asymptotic results that we know about the non-periodic case. And what's feasible, but we didn't look into this a lot. What is feasible is that because this is finite model from 0 to L, that you might, and if you would have an explicit, well, we have an explicit form for all the stationary measures, but if this has some determinantal form, that we might have explicit calculations, for example, for the variance of the number of rings. I think that would be like a first goal if we can do that. And if we would have those exact formulas, then we could exactly calculate, what would happen if you scale it in a proper way in the non-stationary case, and that might give extra information in those settings. Where calculations are maybe harder because of the infinite size of the line. So, it's a bit optimistic, but it's feasible that this could happen.
I see. I think there's also some work, TASEP on the ring and things like that. I don't know if there's any connection.
If you could send me links, then that would be good. Of course, TASEP is related. We know that, let me go back to the beginning. So TASEP is related to this picture, the one that's not turned. And we are looking at this picture. So there's also some difference because, the way you make it finite, the way you make it periodic is different in both cases, right? Here we make the ring like here in this picture, but for TASEP, you would do it in this picture. So you get a very different type of finite model. So I think the finite models are in fact not directly comparable, these two things, because you close the loop in a different way. It might even be that if you make a ring out of this picture, you might not get a solvable model.
I see. Thanks very much. Those papers were by Jinho Baek, but I can send you a link.
Nice, thanks.
Okay, so we have a question in the chat from Maxi. So he's asking the following. So when computing the distribution of the rings, why could you discard the ones which intersected each other?
Yeah, so that's maybe due to the picture I made, this picture. There's in fact no intersection of the rings. They don't intersect. Maybe it looks like that in some places. Maybe, can I see? Here at the bottom, it looks like that, for example, or here. Right? It looks like intersection. In fact, it's not. So this one is actually above this one that goes below here. So there's no intersection between the rings. The rings are separated from each other. And you can really view it as you start with one ring, and then you make the next one, the next one, the next one, the next one, like that. You could do the Markov process like that, and you would end up with the same thing. So that's nice. Now, if I can say one more thing about this picture here, if you, for example, look on the sideline, so a vertical line like this, you will see positive crossings and negative crossings on this line, and they would be above each other. It would be very interesting to know what process is that, because I'm 100% sure that's not a Poisson process. And the reason why I'm so sure is that I know that this is the non-trivial direction. So there should be some cube root things going on. It cannot be Poisson, but I have no idea what it is. So if you look at this vertical line, there should be some attracting or repulsing between positive ones and maybe attracting between negative and positive ones. Yeah, we just don't know. So if someone can find an exact description of that model, that would be also very, very, very interesting. We were not able to do it yet.
Okay.
I have a comment.
Yeah, go ahead, Pablo.
Thank you. Very nice talk, Eric. No, I just wanted to say what was the original model that was proposed to me by Ohad Neufeldheim. And this consists on two zero-range processes in the circle. One is going left, has a drift to the left, and the other one has the drift to the right. And when so we call them positive and negative particles. And so they are independent, but when a negative particle meets a positive particle, they annihilate. Okay, so you have these particles jumping to the left particles, and the other particles jumping to the right, and then they annihilate. And then over that you put creation of pair of particles in nearest neighbor sites, and you create a positive and negative particles going in the opposite direction. So you create in X a negative particle and in X plus 1 a positive particle, and then you have the circle. And so if you rescale that in a correct way, you will get this deterministic process that Eric was talking about.
Yeah, the only problem is that, so this is a discrete model that Pablo was describing, and the rescaling to get to the PNG model is not the most interesting one for that particular problem. But we were not able to find stationary measures for the discrete case. That turned out to be out of reach somehow. And also there's some issue there that how do you choose the position where you put the negative and the positive particle, and and what do you do if they end up in places where you already are? So you have to make some choices, which are maybe not canonical. And so the discrete version is more difficult than this continuous one. But the continuous one looks more familiar to the people with, who know the Hammersley process and those.
So I was about to make a question related to what you just mentioned, etc. So if instead of taking the, it seems to me that you can do a similar construction in discrete. So you take instead of continuous circle, the discrete circle, and you put the Poissons and you do the rings. I mean, it seems that a similar construction could be possible, no? And maybe it has the same properties.
I think that's what Pablo is describing basically.
It's different a little bit.
Process. But as we said, we couldn't find any stationary measures for the discrete case. So somehow it seems.
It seems that the Milton is talking about deterministic motion, right? In discrete, is that it?
Yeah, exactly. So I mean, just thinking about the rings, so yeah.
But then the time is also discrete.
No, not necessarily. No, so time is still continuous. But
when do they jump?
Well, they like random walks, no? That they go.
So so that's not deterministic. They have a drift. Let's say they jump at certain rates to the next side. So I think it's very similar to what Pablo was saying, and so there. And I also think there are several ways to approach this and make choices, but we couldn't think of a way that we could actually solve the stationary distribution for that. So. You know, if you would be able to do that, it would be even stronger, because this continuous case is a limit of the discrete case. But you know, we tried some geometric things, and you know, we tried, I think, the obvious candidates, but it didn't work out.
Okay. Okay. Well, if there are no more questions, maybe we can thank Eric for this very nice talk.
You're very welcome. It was a pleasure.
Really.
So, and then see you next week, right?
I'm not sure if I'll be there, but
Thank you, Eric.
it's a pleasure to give this talk. And nice to see a lot of you again.
Okay.
Yeah.
Yes.
Okay. Bye-bye.
Bye bye.
Bye.
Thank you.
Bye, everyone. Sergio.